term, is there? C is negative 3. So this is 0, and your a is 1. So x equals 0. That means it goes right down the middle for this one, right? That's where our vertex lies. So vertex here, x value 0. Okay, we plug 0 in. Go to the right couple, go to the left couple, plug in that 1 squared minus 3, negative 2, plug in 2 squared minus 3, that's 4 minus 3, or 1, and so on. Okay, plug in negative 1 squared and negative 2 squared. And we put those on. 0, negative 3, there's our vertex. 1, negative 2, 2 comma 1. And now don't forget this thing has got to be dashed. Okay, this thing is dashed. Right? So we got this dashed boundary line. Now let's go ahead and let's pick a point, and this time, you know what, let's pick one that's outside of this boundary line. Like let's pick 4 comma 0 to test. How does 4 comma 0 work out? So number 2, let's test 4 comma 0 in y is greater than x squared minus 3. Well, our y is 0. Our x this time is 4. 4 squared minus 3. 0 greater than 16 minus 3. Is 0 greater than 13? No, this is false. Okay, it happened to be false. Had it been true, I'd shade that side, right? But it's false. So I end up shading in there. Now, this is a system. So that is asking us, where are all the solutions that satisfy both of those inequalities, both of those original inequalities there, right? So in other words, you got to find their intersection. Well, where's the intersection? You see where it's both blue and green? Right in here. Right in here it's blue and green. And then the question becomes, well, do I include the points on a solid line? Like this vertex right there, is that a solution? Yes, because it's on a solid line. In other words, it works for the blue one, but it also works for the green one. You see how that's inside the green portion there as well? Now, if it's on a dashed line, it does not work. So let's take that point right there. Sure, that satisfies the blue portion, but it does not satisfy the green portion, because on that green portion, it is strictly greater than, right? It is strictly greater than. So it would give you a false if you were to plug a point in from a dashed line. Okay. For instance, in fact, let's plug in this vertex 0, negative 3. Why doesn't that work? Well, if this is 0 and this is negative 3, is negative 3 greater than 0 squared minus 3? No. Is negative 3 greater than negative 3? No, it's not greater. So that's why you cannot include points on the dashed line. And of course, all these points in here in the red, right? Those are all points. Okay, so that's how you graph a system of inequalities. A system of inequalities. Now, the last thing that we're going to look at in this section is solving quadratic inequalities algebraically. Okay, so solving quadratic inequalities algebraically. I'll give you an example. Let's say you got x squared plus 5x greater than or equal to 6. Okay? X squared plus 5x is greater than or equal to 6. Well, we still do the same thing that we did when we were using like the quadratic formula and things. We want to get one side equal to 0. Okay? So let's go ahead and take this 6 over. And you got this x squared plus 5x minus 6. Or I should say what you do for pretty much any method when you're solving quadratics is, well, that's not totally true, completing the square, but when you are solving quadratics, you get one side equal to 0 most of the time, okay? Because you're at this point, and then you can choose whether you want to factor or whether you want to use the quadratic formula and so on, right? Or proceed with maybe completing the square, okay? So anyways, we're right here, and I say, you know what? At this point, what I want to find is I want to find what we call critical points, okay? I want to find critical points. In other words, the x values for which this is true. So we imagine this to be equal to 0 for a minute and find the x values for which this is true. And we go ahead and we solve the, let's do the easy way here and just factor this. So 6, 1. Okay, check that, x squared minus x plus 6x minus 6, all that works, all right? Use that zero product property. Say, okay, subtract 6 both sides, add 1 both sides. Those right there are what's called my critical points. Critical points, okay? So negative 6 and 1. So I'm going to put those on a number line. Negative 6 and 1, okay? And then the question becomes, well, when I'm looking at this negative 6 and 1, and I'm going to test to the left of this negative 6. Okay, so this is kind of division area. This is a division area, these testing points. I'm going to test to the left of negative 6 to see if anything out here is true, and I'm going to test in between. I'm going to test the next value in between. I'm going to test something to the right of 1 as well and see where my solutions lie. Okay? And the critical points must also be considered as solutions as well. In other words, if you plug negative 6 in, is it true? You know, and if you plug in 1, is it true? So that is determined by the greater than or equal to. If you have an or equal to, you include, okay? You include that as part of your solution. And you're also going to include that. And if you're not sure, just plug it in, like plug in the 1. 1 squared plus 5 times 1, 1 plus 5 is 6. Is 6 greater than or equal to 6? Sure, it's or equal to 6, isn't it? Okay, so the negative 6 and the 1 is included when you have an or equal to sign on these. Okay, so the critical points will also be part of our solution. Now we got to figure out, okay, what x values are true. So let's test something to the left. So like negative 7, test something to the left there, and we're plugging it in to this original. So negative 7 squared plus 5 times negative 7. Is that true? It's 49 minus 35 greater than or equal to 6. Is 14 greater than or equal to 6? True. True. That means yes, that's part of our solution, right? Okay. And then you can test something over here like x equals 0, we'll say. Is that true? 0 greater than or equal to 6. False. False. And test something to the right like 2. Okay, you plug that in. 2 squared plus 5 times 2 is 4 plus 10 greater than or equal to 6. Sure, 14 is greater than or equal to 6. True. All right? So true, false, true. So then you end up writing your solution as x such that I have anything to the left or equal to negative 6 or greater than or equal to 1. Okay? So you see how that's to the left of negative 6, and then this is to the right of 1. So any of those x values is what this solution is saying. Okay? Or if you want, you can use interval notation. Say negative infinity up to this negative 6. I include that. Union, and then go take off from this 1. And you go 1 to positive infinity. That's an interval notation for saying the exact same thing. Okay? Now, graphically, I wish I could pull up my graphing calculator on this, but it's in a window right now. But that's how you're going to approach solving quadratic inequalities algebraically, okay? To review, you get your critical points. You determine if they're solutions or not. You test on each side of the critical points, okay? And then finally, you you just write the solution wherever it's true. You're including those x values, okay? So let's do one more. All right, where is that greater than 0? Okay, let's go ahead and, oops. Let's get the critical points. Okay, so we make sure get one side equals 0. It already is, there it is, factor. Okay, so there's our critical points, 3, 3, and -1, right? 3, 3 and -1 are our critical points. Now, do we include them or not? Do we include them or not? Well, let's see. If you have plugged in, let's plug in 3, right? Now you see how it's just simply greater than? This is not going to be included. In fact, let me use this sign. That means open. That means, if you remember open hole, that means I do not include that. Do not include that. In fact, that's what I really should have used on this other one. I should have said these are included, so I should have filled that in to represent that I'm including those. I'm including those on that other one. Okay. So -1 and 3, we're like, okay, we're not including that. Again, your check on that is to plug it in. Is 0 greater than 0? False, right? Plug in -1, it's going to end up being false as well. Okay, so I say I cannot include the points, but that is where it's going to split for me, right? So I'm going to test like something to the left, -1. How about -2? Let's test something in between. We always like 0. And test something over here like maybe 4. Okay? And we test them. And that's true, isn't it? True. True. So that's going to be part of my solution here. You plug in 0. False. Okay, you plug in 4, test 4. Blah, blah, blah. Ends up being true as well. Okay. Now let's write our answer. How do you write this? Now can you see, whoops, let me go back up here. Can you see how it's all x values to the left of -1? So to the left of -1, right? And all x values to the right of 3 in this case. Okay? So how you write that in set notation is say, well, x such that x is less than -1 or x is greater than 3. Okay? Or you could say -infinity up to that -1. I do not include it. Union, I take off from 3 to positive infinity. That's another way of writing that. Okay? Now, in this case, you notice, what if it had been false, true, false instead? In this case, you had, what was it, -1 here. You had 3 here. Okay? So you're inside there. Okay, and these were not including. Well, if you remember when you're writing that, you got to write that as a compound inequality. Okay, that's just to remind you there. Or if you want to write that in set notation, you can say that's from -1 to 3. Or I'm sorry, in interval notation. The first one's set notation, the second one's interval notation. Thanks for listening. Good luck.